We start the lecture Physics for Electronics. During this lecture I give you the information about electromagnetism. So the main subject of this lecture will be electromagnetism, electrodynamics and uniform plate wave. The word electricity came from ancient Greece, and ancient Greece, they know the phenomenon that consists in the feature that if we make rubbing of amber with different material, we can notice the forces, attractive or repulsive forces, that depend on the kind of material that we use. Amber in Greek is called electron. So the phenomenon is electricity, that means that phenomenon connected with electron, with amber. As we see during the lecture, electron is the source of electric field and as well the source of magnetic field. So this is very, very important particle, and we should learn as much as we can about the electron. Today, standard model is commonly used, but for our lecture, it is enough to model of the atom that was proposed by Bohr, and we discuss this model. This is the nucleus of the hydrogen, and here we have the orbit of electrons. In hydrogen we have only one electron, and the nucleus consists from proton. The diameter of proton is in the range of 10 to minus 10 meter, when the diameter of the orbit of electron is 0.53, 10 to, no, here is 10 to minus 15, and here is 10 to minus 10. Just from this picture and this value, you can see that it is not in scale. To have this picture in the scale, I should make the orbit of electron at the distance of 1 kilometer. So electron is rotating around the nucleus at the distance of the radius of about 1 kilometer. So we can see that here we have vacuum. It is empty. Universe is empty in the scale of atoms. What next? What is the velocity of the movement of electron? Of course, this is not only in one plate. It changed the plate, so it creates a sphere. Electron during its movement around the nucleus creates a sphere. and the velocity is very high. The velocity of movement is 2.2 10 to 6 meter by second. Of course, such velocity is impossible in air, but in the scale of atom we have vacuum, so we can have this velocity of the movement of electron. And how often what is the number of the surrounding of the nucleus during 1 second. But during 1 second, electron rotate surrounding nucleus 6 to 10 to 15 times by second. So we can see that we have the sphere of electrons, because so much often he rotates around the nucleus that it creates a sphere. And let's write the feature of electron. Today we can write the mass of electron. It was measured in different experiments, and we know this mass with quite high accuracy. This 9.1, only two first digits is important, kilogram. This is the mass of electron. Mass of proton is 1080 mass of electron, and mass of neutron, mass of electron. Mass of electron is not important for us. Much more important is the charge. And charge of electron is equal 1.6 10 to minus 19 Coulomb. And with minus, this is minus because why electron have minus? It came from the time of Ampere, when Ampere defined the electric current. He decided he made definition of electric current that this is the movement of positive charges. When it was discovered that in metals the current is the movement of electron, and these electrons are moving in opposite direction than direction of current. So to make this definition of current correct, electron should have negative value of the negative sign of the charge. Today we use this 1.6 10 to minus 19, and this is the charge of electron. And this is the minimal portion of the charge. So we can say that charge of electron is quantized. That means that charge, we can have charge in the portion, and smallest portion is portion of one electron. Somebody can tell that quark, for example, quark have 1/3 of the charge of electron, but free-standing quarks have never been observed, because quarks at once they are gluing together, creating proton and neutron. So standing free quarks can't exist. So the only stable minimal portion of charge is charge of one electron. And electron have the property that we call spin. Spin of electron is 1 second. That means for particle, if particle have spin equal to 1, for example, I have spin equal to 1. That means that if I rotate one time, I look the same. For electron that have 1 second spin equal to 1 second, we have to turn electron to time. So if I will be electron, I should rotate to time to be the same. So this means that the spin is 1 second. And spin of electron is equal to, this is the Planck constant, and it is 105 10 to minus 34 joule multiplied by second. Another feature of the third feature, so first this is the mass and property of, second is quantization, and third relativistic invariance. Relativistic invariance means that with velocity, charge doesn't change its value. We know relativistic formula of Einstein, that mass with the velocity changing its value. This is the standing value of the mass, but if the velocity is going to be close to velocity of light, the mass is going to be to be big, to came to infinity. For charge we have that Q, even with very high velocity, is equal to standing value of the charge. Q is letter that we apply for the charge. And next feature of the electron is so-called conservation of charges, so of the law of conservation of charges. The law of in isolated space. Isolated means that charges doesn't pass inside and as well do not pass away from this isolated part of space. In this isolated part of space, algebraic sum of charge can't change. So we can write that sum of all charges existing in this isolated space will be always the same. And this rule, this law, is very important because we can apply this law even from the beginning of universe, from the Big Bang, when everything starts. At this moment, the sum, when the universe was small, the sum of all charges that were at that time was constant and was equal to 0. Is equal to 0. That means that sum of the number of positive charges and negative charges is the same. The number is the same. And there is no phenomenon in which we can destroy the charge. For example, we want to destroy electron. We can't destroy electron because this will change the sum. So if we are destroying electron, for example, annihilation of electron, at the same time we have to destroy positron, anti-electron. So the sum, algebraic sum, will not change. And the same we have for all phenomena in physics, that we can't find phenomena that destroy only one kind of charge. Later we knew that electromagnetic forces are much stronger than than gravitational forces. So from this knowledge we came to the statement that in the universe, for example, in all galactics, the sum of positive charges and negative charges is equal to 0. Because if not, the forces of electricity will be able to notice these forces, and these galactics will explode with these forces, that they are much stronger there than gravitational forces. And finally, one can ask, but what about the dimension of electron and how it look like? And this is a very challenging subject in modern physics. Nobody knows how electron look like, and nobody knows what are the exactly dimension of electron. In some experiment, observation of single electron in panic trap, this is special devices that is called in the experiment with panic trap with single electron, we find that dimension of electron is in the range of 10 to minus 22 meter. So this is the very small dimension. But exactly we don't know, and we don't know how electron is looking like, because nobody have idea how it look like. We don't know if electron is particle or it is wave, because in some experiment it behave like particle, in another like particles, like wave. Electron can interfere one with another, so they behave like wave. There are some phenomena where it behave like wave, for example tunneling, so-called tunneling effect, and in this effect electron behave like wave. So we know everything about electron, and now let's learn about charges. We can have different configuration of charges, and we will apply mathematical model for these charges. The first model that we apply is point charges. And this is the mathematical model. Point charges the dimension of the charge is going to 0, and to avoid mathematical or physical problem, we do not take into consideration the dimension of the charge. We consider that the charge, all charges is in the point, and dimension of this point can be neglected. We describe charge with letter Q, and for example this is Q1, and here we can write the position of the charge. This is in Cartesian coordinate system. X1, Y1, Z1 and Z1. For example, 10 microcoulomb in the point 102. This is the Q1. Value in Coulomb and as well the coordinate where we can find this charge. If we have more than one charge, we can say about charge distribution. And in this case we can say point charges distribution. If we have here Q1, Q2, Q3 and so on, the total charge is very easy to find. This is the sum of I equal to 1 to n Qi. This is total charge that we find in this volume. This is point charge distribution. Of course, physically only electron is exactly, if we have here the electron, we can say that this is a mathematical model that describes precisely the point charge. But electron is very, very small, very little part of charge. Usually we will be speaking about microcoulomb, and in microcoulomb we have a huge number of electrons that must be in very small point. Continuous charge distribution. We know that charges can be distributed like point charge, and this point charge this is create discrete charge distribution. But charge could exist in different way as a continuous charge distribution, and we can have three kinds of continuous charge distribution: line charge distribution, surface charge distribution, and volume charge distribution. We start with line charge. Let's have very thin wire, very thin line, and the diameter of the line phi we can be neglected, so we do not take into account the diameter of this wire, of this line, and the length of the line is L, big L, and now on this line we have the charge. The charge has continuous distribution, and we have to define line charge density. Line charge density. Definition. For light charge density, we reserve letter tau, Greek letter tau, and density in point x, y, z is defined like dq divided by dl. Unit is Coulomb by meter. Here we take differential distance dl, and on this distance there is charge dq. And density, here we have points x, y, z. So coordinate of this point is x, y, z. So the charge density in this point is equal to this value. When we have a distribution of line charge, we can calculate total charge that we have on this line. Total charge, big Q, we can calculate from formula. This is line integral from tau dl. I take this in rectangle, that means that you should know this formula. For the case that we have uniform charge distribution, calculation of total charge is much easier. For uniform distribution of the charge, total charge is equal tau multiplied by R. This is for uniform. Of course, the unit of charge is Coulomb. This is for line charge distribution. This is the first case of continuous charge distribution. Second case is surface charge. In this case, we have thin sheet on which charge is distributed. The space of this thin sheet D can be neglected. We do not take into account this space. It is very, very thin, and we defined charge density. Surface we take a small differential piece of the surface, and here we have dq. This point have x, y, z coordinates, so sigma q in the point x, y, z is defined like dq divided by ds. Unit Coulomb by metr squared. When we knew the function that describes density, surface charge density, we can calculate total charge Q from formula. This integral is called surface integral. This calculation we did in Cartesian coordinate. Of course, for some cases it is much easier to use another coordinate system. The result is in Coulomb. And for special case, when we have uniform charge distribution, total charge can be calculated from much simpler, in much simpler way. We multiply sigma q by s. S is surface on which we have the charge. And finally, volume. Volume charge distribution. In this case, we can imagine, I think that everyone knew this, when we have the piece of material, we can, and this volume, this is piece of volume, and it is charged. We can define the charge density we take differential piece of volume dV, and in this piece of volume we have differential charge dq, and x, y, z are the coordinates of this point. We can consider this like a point because dV means that it is very small portion, very small piece of volume. Rho v in the point x, y, z is defined like as we see, the definition of the density of continuous charge distribution are very similar one to another and very easy to remember. Like before, we can calculate total charge from formula. This integral is called volume integral. The result is in Coulomb. And finally, when we have uniform charge distribution, total charge is calculated from formula ρ multiplied by φ Coulomb. And now we can discuss about physical aspects. This uniform charge distribution, this volume charge distribution, is the case that corresponds exactly to the physics, because usually, if we take into consideration that the total charge is a huge number of point charges, electron for example, so they create volume charge distribution. So this corresponds exactly to the physics. But where we can find surface charge distribution and line charge distribution. Surface charge distribution we can find when we charge metal, for example, conductor. When we charge conductor, the charge, the only stable position of the charge is on the surface of this piece that we charge. And we can have uniform distribution only on the ball. When we have the ball of conductor and we charge this ball, we obtain uniform charge surface distribution. When conductor have different shape than the sphere, we do not obtain uniform distribution. Charge will be distributed not uniform. Line charge distribution we can have when we for example take very thin wire and charge it, so we have the line charge distribution. For example, for the calculation of capacitance of the line, that is that we have, for example, line over the earth, we charge this line with this line, and we will calculate the capacity using the line charge distribution. Coulomb law. We can say that modern electricity start from this year 1785, because this is the first formula that describe the physics of the electricity. Coulomb was not the first. Galvani propose similar formula 15 years before Coulomb, but he was not sure that his calculations are precise, so he do not publish his result. Charles Coulomb was the officer of French army, and he was more technical than military man, and he invented very precise system for measuring the weight, the balance. And with this balance, it was the differential balance. He measured the forces and write the formula that describes the forces between two charges. We can say that he was very precise, because at this time he was able to write coefficient in formula with accuracy of 1 digit. He started from Newton law, because 100 years before Coulomb, Newton wrote his law of gravity, and in this law he wrote that the force that attracts to mass is inversely proportional to the distance between this mass. The same assumption had taken Coulomb. So he assumed that the force will be inversely proportional to the distance between the charges. It was only problem to find, the challenging problem was to find the coefficient of proportionality. And he find this coefficient. Today we know that the Coulomb's law is correct with the accuracy of 11 digits. I will write the Coulomb's law in vector form, because vector form gives us more information than scalar form. F12 is equal 1 divided by 4 p epsilon 0, Q1, Q2, force is in newtons. And now let's write what we have in this formula. Let's take Q1 in this point and coordinates of these points are x1, y1 and zy1. In point 2 we have the charge Q2, x2, y2, z2. We connect these two charges with vector R. This vector is very important. R1, 2. Vector 1, R1, 2 connect the charge Q1 with charge Q2. Q1 is the source of the force. And here we analyze effect of this force. So the vector of the force start in point Q2, and here we can write that this is 1, 2 force. What we can see from this sketch? Q1 is the source of the force, and Q2 is the charge on which the force is exerted. If we exchange that now Q2 is the source of the force, here we should write in this way, force 2, 1. And vector R, how to find vector R1, 2? This is x2 minus x1, y2 minus y1, and z2 minus z1. This is the value of vector R1, 2. Here we have the up to vector module of vector R1, 2 up to power of 3. So how to calculate module? We calculate the module of vector 1, 2, R1, 2 in this way. And finally epsilon 0. This is the constant. We know this constant with accuracy of 11 digit. And this is permittivity of free space. Permittivity of free space. Vacuum, we can say this is permittivity of vacuum. And it is equal to 885 10 to minus 12 farad by meter. This value is important. I will take this in that angle, and as well the unit is important. It is farad divided by meter. Farad. Farad is the unit of the capacity. Now we have all data that correspond to this formula, and what information we can take from this formula. First of all, we see that the direction of the force depend on the sign of the charges. When the charges are alike in the sign, the force is repulsive. When the queer and Q are alike like in the sign. We have repulsive force sources. When Q1 and Q2 are different in opposite sign, we have attraction. We have attractive forces on or attraction of two charges. And we can easily see that force 1, 2 is equal to force 2, 1. Because we only change this Q2 with Q1, so it is easy to find that F12 is equal to F21. Coulomb's law was the first formula that describes electric field, so we can say that this is the start of modern scientific description of this phenomenon that we called electricity. But what happened if we have more than one electric charge in the space? In this case, of course, we have to make the sum of these forces. We write these two. Let's have two charges, Q1 and Q2. Q1 and Q2. And we want to calculate the force, the total force, because now we have two forces. One force is F10, and second force is F20. The total force will be this force, Ft0, total force exerted on Q0. We see that total force is equal to but this is the vector sum. Very important that we do not make this like algebraic sum, but we have to make vector sum. For two discrete charges, it is easy to calculate. But what about if we have, what happens if we have here more charges, or if we have, for example, charges like this, with sigma q, continuous distribution. The calculation of such cases is much more complicated, and it is much easier if we find here the state of the volume of the space in this point, and we defined the electric field intensity in this point. electric field intensity. Definition. For electric field intensity, letter E is reserved, and electric field intensity in the point x0, y0, z0, where in the point where we find q0 is defined as a total force exerted on charge q0 to the value of q0. But special q0 must be positive. Q0 is positive. And q0 is small. We can call it probe charge, test charge with small value. It is important for some cases because it should be small to not change the testing field. And we see here the additivity of the Coulomb's force, exactly the same we have for electric field intensity. So the total electric field intensity is the sum of vector sum of all sources of the electric field, but the sum have to be made in for vector. This must be vector sum. For one charge at the distance of r, using this definition, we can very easily find the electric field intensity. At the distance of r, using this definition and Coulomb's law, we can easily find electric field intensity. I will write once this value. It is 1 for P epsilon 0 Q divided by R Here we write from Coulomb the force exerted on Q0 and divide by Q0, so Q0 disappears from here and we have such formula. And here we should write this. The unit of electric field intensity is volt by metr. From this definition we see that it should be Newton by Coulomb. But after changing we find that this is the volt by meter. And please remember this, because we always check the correctivity of our result, checking the unit. So this is the value of electric field intensity at the distance of r from the charge point Q. We see that the same electric field intensity we will have here and here. Module of the intensity will be the same. Only direction will change because vector r changes will be changes on this point on the surface. During the exercise, we will calculate the electric field intensity from different charge distributions. Of course, this is not easy for example, when we have charge distribution like this and we want to find electric field intensity in this point. It's not easy, but we will use special distribution, very symmetrical, to make this calculation easy and it will be as well easy to understand how we calculate this. And finally, streamlines and sketches of the fields, of the field. we have here electric field. Electric field we can define. Electric field is the vector field. That means that every point surrounding the charge is defined by the value that is vector. This could be the simple vector or function or vector function, vectorial function. This space is called the vector field. And as an example of such fields is electric field, gravitational field, magnetic field, and so on. And as well we can have scalar field. Scalar field we have when for every point in the space we can describe this field with scalar value, real number or real function. If we have real value, real number, we have scalar field. And the example of such field: potential distribution, electric potential distribution, gravitational potential distribution, temperature, mass density, charge density. Everything of this value create scalar field. Let's return to vector field because it is much more interesting for us. And it will be very nice to be able to see this field. unfortunately, there is no physics phenomenon that allow us to see the electric field. So we should pass to the special system that allow us to make the sketches of the field. Streamlines of electric field. Let's make the rule. We put in the field, in the space, charge Q0 and let him free to move. In the case that we have positive charge in this point, such charge, positive Q0 is probe charge, test charge, positive and small. It will move thanks to the Coulomb forces in this way. From this point, in this way, this way. So we can make the sketches that show us how the Q0 will move. And this is the sketches of the field. We consider this as a sketches of the field. For two charges, Q1 positive and Q2 negative, we have the sketches like this. The line of the field will be like. And direction is in this way. This way we can make the direction of the line. For two positive charges it is a little more complicated because the line have such shape. I think that everyone is able to do such pictures, and there are special methods to calculate the electric field intensity if we know the line distribution.